Hello, this is Jack Jackson. In this video, we're going to be talking a little bit about the summation formulas that you see here on the screen. And we're going to actually go through some quick proofs of these things. And we're going to use these in the next video to evaluate a definite integral exactly from the definition. Okay, so this first one here is the sum of n times a sub k is n times the sum of a sub k. That's nothing more than the distributive property. You know, the first term is n times a1, then the next one is n times a2, the next one is n times a3. They all have a factor of n. You can factor that out front and just add up the a1, a2, a3, and so forth, and then multiply by n. That's what that's saying. So that's a direct application of the distributive property. In fact, it's a statement of the distributive property. The next one is really just the definition of multiplication. The sum from k equals 1 to n of c is n times c. In fact, that's what's meant by n times c. What does 3 times 4 mean? It means 4 plus 4 plus 4. And here what do we have? We have c plus c plus c, and n of those, so that makes n times c. The third one says is a repeated application of the commutative and associative properties. And if it's a finite sequence, a finite series like this, we can, in fact, do this. And so, for in other words, if you have a1 plus b1 plus a2 plus b2 plus a3 plus b3, you can reorder it so you can add all the a's together and add all the b's together and then add those two sums together. That's what that one's saying. So, not much proof needed on those. Number 4 is a specific example of a sum of an arithmetic series, and I'm going to actually write down the proof for you right here. Okay, so we have S is the sum from k equals 1 to n of k, which is 1 plus 2 plus 3 plus 4 plus 5, all the way up to n. Notice the 1 right before the n would be n minus 1, and before that's n minus 2. Now we're going to reverse the series so that we can see it as the sum from k equals 1 to n of n plus 1 minus k. So n plus 1 minus 1 is just n. N plus 1 minus 2 is n minus 1. N plus 1 minus 3 is n minus 2, until you work it down to the last one when you put it in n plus 1 minus n is 1. So it's exactly the same sequence in the reverse order, and now we just add up term for term. Notice that here we have 1 plus n, so that's n plus 1. N minus 1 plus the 2 is n plus 1. N minus 2 plus 3 is also n plus 1. If you start at the other end, you have n plus 1. Here you have n minus 1 plus 2 is n plus 1. In fact, every one of them is n plus 1. So, but notice that gives you twice the sum if you're adding this up. So twice the sum is the sum from k equals 1 to n of n plus 1, which is just n times n plus 1. That's twice the sum, so the sum itself, the sum from k equals 1 to n of k, is just 1/2 n times n plus 1. And so we get something, we get this here. Now, the more general arithmetic series basically says that if you can do the same exact proof, just write the sequence backwards, and what you get is 1/2 first term, 1/2 n, and then you have first term plus last term instead of n plus 1. That's the part that changes. N1 is the first term, n is the last term. And so that n plus 1 is replaced by first term plus last term. So if it's any kind of an arithmetic series that is a linear function series, that works. So this is a special case of that. If you want to see more about the arithmetic series, I refer you to this video right here in my algebra series. Now the next two properties, properties 5 and 6, can be proved using the principle of mathematical induction. So when we do a proof by induction, it's kind of like climbing a ladder. If you think about it, you need to know two skills to be able to climb a ladder. You've got to be able to get off the ground onto the first rung. And then if you can do that, and then you know how to get from any one rung to the next rung, then we know how to get from the first rung to the second. If we know how to do that, then we know how to go from the second to the third. If we know that, we know how to go to the third to the fourth, and so forth. And so that tells us that we can get up as high as we want. And so that's what we basically do with the proof by induction. We establish what's called the basis case, which is typically to show the theorem is true when n equals 1. That's like getting on the first rung. And then we show an induction step so that we prove that if we assume it's true for some, if you've already gotten up a certain level to n equals m, and the theorem is true at that point, then if you let n equals m plus 1, then the theorem is also true there. So the theorem is true for n equals m, implies that it's true for n equals m plus 1. That's like being able to go from one run to the next. And with these two steps, then if we get those established, then we conclude the theorem is true for all natural number values of n. So here's our proof of property 5. The basis case is if n equals 1, then we just have to show the formula is true. Well, now the formula says it's 1/6 n times n plus 1 times 2n plus 1. Now if you plug in a 1 for all the n's, you get this right here. And let's see, this is 1 plus 1 is 2. Of course, that one's 1/6, that's 1, that's 2. 2 times 1 is 2 plus 1 is 3. 2 times 3 is 6 times 1 is 6. 1/6 times 6 is 1. 1 is 1 squared, which is all you get when you sum from k equals 1 to n of k squared. There's only one term there. K equals 1 to 1 of k squared, which is just 1 squared. So in fact, that's all just 1. Okay. Now the induction step. Suppose the theorem is true when n equals m. In other words, we have the following what's called the induction hypothesis. We assume that we know that the sum from k equals 1 to m of k squared, it has this formula where the m is there. 1/6 m times m plus 1 times 2m plus 1. So if we assume that is true at some level m, we have to show that that's going to make it true at one level higher. So we're going to let n be m plus 1, and we want to show that this sum from k equals 1 to n of k squared is this 1/6 n times m plus 1 times 2n plus 1. So n is m plus 1, that's just substitution. Now what you do here is you split off the first m terms, collect them together, group them, and then split off the last one, which is just m plus 1 squared by itself. Now this sum of the first m, we have assumed here that it is that this formula is valid. That's our induction hypothesis, so we can replace that by that formula. Next, I'm going to do some factoring. I'm going to factor out a 1/6 and an m plus 1 using the distributive property. So we're essentially multiplying this by the reciprocal to get this. So we're multiplying by 6 over m plus 1. The 1/6 cancels here, the m plus 1 cancels, and we're left with m times 2m plus 1. The second time, we've got a 6. 1 divided by 1/6 is 6. And the m plus 1 squared divided by m plus 1 is m plus 1. Check it out. If you multiply this out, you get 1/6 m plus 1 times m times 2m plus 1. That's the first term. And 1/6 times 6 is 1. And then you got an m plus 1 squared for the second term there. Okay? Now I'm going to use the distributive property again, but this time not factoring it out, but multiplying it out right here inside this parentheses. So I still have the 1/6, the m plus 1. m times 2m is 2m squared. M times 1 is m. 6 times m is here, and 6 times 1 is 6 here. Combine like terms in the middle, we get 7m. Now we want to factor this, basically FOIL factoring backwards, or anti-FOIL factoring, which is really just a more complicated version of the distributive property. And so we get 2m plus 3 times m plus 2. Check it out. 2m times m is m squared. 3 times 2 is 6. This gives you 3m plus 4m is 7m. So that's correct. Now we want to rewrite things and substitute back in terms of n, but n is m plus 1. So this is just 1/6 n here. But what about this? Well, if I think of this as m plus 1, 2 times m plus 1 is 2m plus 2. And if I add another one, I get 2m plus 3. So this is 2 times m plus 1 plus 1. Check it out. 2 times m is 2m. 2 times 1 is 2 plus 1 is 3. Similarly, I could write m plus 2 as m plus 1 plus 1 more. You can see that's m plus 2. And all these m plus 1s are just n. And sure enough, that's the formula we wanted. I think I switched these, maybe switched these two terms right here, but it's the same thing. So we showed that the theorem is true for n equals 1. And we showed that if we know it's true for any level, then you can go to the next level up. So we showed this true for 1, and this says if we can do it for 1, we can do it for 2. If we can do it for 2, we can do it for 3. If we can do it for 3, we can do it for 4, and so forth. If we can do it for any level, we can do the next one up. And so the principle of mathematical induction says the formula is valid for all natural numbers n. Now property 6 is very similar. Proof by induction again. We're going to let n equals 1 and notice that the formula is true. So here's our formula, 1/2 n times n plus 1 squared. It's kind of interesting when you look at this that, in fact, the formula for just summing the, where is it, right up here, the formula for just summing up k is 1/2 n times n plus 1, and the formula for summing up k cubed is the square of that. So that's kind of an interesting little result. So anyway, where were we? So we take that formula with the square, and we plug in n equals 1. So 1 here. 1 plus 1 here is 2, times 1/2 is 1, times 1 is 1, and so we get 1 squared. But 1 squared is 1, which is also 1 cubed. And the sum from k equals 1 to n of k cubed then is just k, n is 1. So it's only one term here, which is just 1 cubed. So all of that's just another fancy way of saying 1. So the theorem is definitely true when n equals 1. Now the induction step is we suppose the theorem is true when n equals m. In other words, we assume this induction hypothesis that if we sum from k equals 1 to m of k cubed, we get 1/2 m times m plus 1, whole thing squared. Now let n be m plus 1. So the sum, we sum from k equals 1 to n of k cubed, it's the sum of k equals 1 to m plus 1 of k cubed. That's just substituting n equals m plus 1. And once again, like the last proof, we split off the last term where the index k is m plus 1, so we get m plus 1 cubed, plus we got all the other ones from k equals 1 up to m. So this group together, this sum from k equals 1 to m of k cubed by our induction hypothesis is 1/2 m times m plus 1, whole thing there squared. Plus, then we still got this last term here, m plus 1 cubed. Now notice these, well, first of all, I want to square this out. If you got a bunch of things multiplied together and the whole thing squared, we can put the square on each one. 1/2 squared is 1/4, and we got m squared, and here we have m plus 1 squared. Notice they both have an m plus 1 square, and I like to get rid of the fractions, put them out front. So I'm going to factor out a 1/4 m plus 1 squared. So when I divide out, this cancels, this cancels. The only thing left is this m squared. And then over here, the m plus 1 squares cancel. I'm left with the m plus 1 and a 4. So check it out. 1/4 times m plus 1 squared times m squared is what I have for the first time. 1/4 times 4 is 1. M plus 1 squared times m plus 1 is m plus 1 cubed for the second term. So it does work. That's really nothing more than just the distributive property used in a factoring situation. Now I use a distributive property the other direction by multiplying this out here. This 4 times m plus 1 becomes 4m plus 4. Then I factor this trinomial, which turns out to be a perfect trinomial square. So it factors as a binomial squared. It factors as m plus 2 squared. Remember, check it out, or use FOIL if you'd rather. M times m is m squared. 2 times 2 is 4. Multiply, we get 2m for both the outer and the inner product. So that becomes 4m for the middle. Now, these all have squares. That's a square, that's the square of 1/2. So I can basically put a square outside and think of this as 1/2 squared. M plus 1 squared out here. M plus 2 squared outside. Now, we want to get things in terms of m plus 1, and this one already is m plus 1, but I rewrite m plus 2 as m plus 1 plus 1 more. And sure enough, now if we substitute n equals m plus 1, we get 1/2 n times m plus 1 whole quantity squared, which is what we set out to prove. And again, this second part proves that if we know it at one level for n equals m, we can prove that the theorem is true, the formula still holds when n equals m plus 1. That, along with our basis step, is enough to say that the theorem is valid for all real numbers n. In our next video, we're going to use these formulas as important steps. You can see right here in the middle of this proof. We'll use the sum of k cubed right there that we just proved, the sum of k squared here, the sum of k, and the sum of 4. And that's going to be an important step right in the middle of the proof in our next video.